kind of a halfway joke for English is that so many times in life, we think we're always right. We're not always right. You have to look at things from other people's point of view or other people's perspective. So if I'm over here, that looks like a 6. If I'm over here, it looks like a 9. So sometimes we're both right. The point is that you have to be professional and you have to be nice in life. So please be considerate of other people's point of view, so to speak. Just like last time, if you need any continuing education credits, you're welcome to use these numbers to get that. What this talk is going to be all about is testing, adjusting, and balancing. And we're going to do both air and water. To start off with, we do the air side, testing, adjusting, and balancing. And I'm going to say tab. I'm going to say tab a lot because I don't want to have to say testing, adjusting, and balancing all the time. So that's what I'm going to do. In the air side tab, we have basic measurements. We have lots of instruments. We're going to talk about balancing, fan laws, and then finally getting into calculations. Testing, adjusting, and balancing tab is really very much a math profession. So we use a lot of math. So typically, you know, in the air side tab, we're looking at exhaust fans, we're looking at air handling units, we're looking at ductwork, that sort of thing. We see a lot of that, and we do a lot of that. So these are just typical examples of mechanical rooms where you would see air handling units with ductwork and dampers and all that stuff that we typically work with in the field all the time. Switching gears to the water side tab, which we'll do in the second half of this talk, that's obviously all about water and pumps and GPMs and those kind of things. So we're going to get a lot into pumps and pumping, a lot of water balancing prep, psychrometrics, calculations, pump laws, instruments, and a lot of that. Here are some just simple examples of going out into water chillers and looking at water chillers and piping, trying to figure out how they work. This is an air side chiller example where, you know, we're looking at balancing the amount of water that flows through a chiller, through intricate pumping systems and things like that. But that's a lot of what we're going to talk about. What happens in the field is a lot of work. A tab technician or a tab engineer, they do a lot of work, and it's not easy work, it's hard work. So I always say that they are very, very hard workers. But the team that we typically work with are going to be the mechanical contractor, controls, all the equipment and manufacturer reps, any kind of startup crew from the mechanical or electrical contractor, and then of course the field technician that's in the field, and then the test and balance engineer who's in the office. So there's a lot of moving parts to tab work and a lot of instrumentation, which will show you how that works. The other thing we say a lot about tab is it's really all about the numbers and it's all about the calculations. The engineers of record, they're the ones that create the design and they're the ones that create the numbers that we have to figure out how to get to. That's how we work and that's where it goes. There are many certifying organizations that we report to. No matter what you do in tab work, you need to be certified by one of these organizations. There's a few others, but these are the main ones that are out there. AABC, NEBB, or TAB. Those three organizations, you need to be a member of at least one of them, and you need to maintain that membership annually, which means keeping up with continuing education as well as attending annual meetings and doing the work of the TAB professionals. These are typical icons that we see in the industry. The certification process is a long process, and it's not an easy process. Typically, what happens is you're either certified as a TAB engineer or you're certified as a TAB technician. One of those two is what most everybody does. Obviously, the TAB technician is who works in the field most of the time, and the TAB engineer is who works in the office to support that field TAB technician in the field. That's typically how it's done. But you have to make application, you have to prove education or experience, and you have to continue your continuing education once you are certified. If you do not, you lose your certification, and then you have to go back and start from the beginning. In most of the U.S. states, TAB is required on almost all projects by code. So every project needs to have TAB work done on it in the U.S. The basics of why we perform it, simple. It's like commissioning. You know, it's required by the specification. And in the case of TAB, it's required by code, so that almost all buildings, almost all construction, any kind of retrofits, they have to have a TAB report submitted to the code official before that building can get its certificate of occupancy. It is important, if you're going to work as a TAB engineer or a TAB company, it is important for you to read the specification. Every job has a specification. It says this job shall be tested, adjusted, and balanced by a certified professional firm, blah, blah, blah. But what's different is this. So what's different is, what does that specification tell you to do? And if you don't read it and you get a contract that says you need to do all this stuff and you did not account for it in your bid or in your proposal, you will have to do it for free. And TAB work is not cheap. It's not cheap. And for example, this thing here, very important. Many specs, especially existing building, they say, hey, you need to pre-balance the existing systems to determine their functionability. Why? Because at the end of the job, people will say, well, it never worked in the beginning. We can't make it work because it never worked in the beginning. Well, so what happened? The engineer says, okay, fine, that's fine. So now you need to pre-balance it in the beginning, so you can't say that anymore. I mean, that's where that came from, right? People yak, making excuses why they can't do their job. Many specifications require duct and pressure tests as the project goes along. So as you install 1,000 feet of pipe, you need to test it. As you install 1,000 feet of ductwork, you need to test it. And if you don't, then it costs a lot of money to go test that ductwork and piping when the ceilings are up and when it's buried underground. So you need to pay attention to what the specification requires. Opposite season testing. In Thailand and Florida, we don't care. But let me tell you, in New York and Chicago, you care. Because it's very hot in the summer, very cold in the winter, and so you have to come back and test that in the opposite season. Sound and vibration, very expensive. Controls and building automation verifications, life safety testing, fire smoke dampers, all of this, very expensive if you do not account for it in your original proposal or bid. So it's simple. If you're going to bid a job or you're going to make a proposal, you need to read the specification. I know it sounds simple, but I can tell you, many people tell me, oh, well, I didn't read that, or, I didn't mean that. Well, sorry, you have a contract, you're going to end up having to do it. The other thing that's important in any tab job is you need to constantly keep track of the deficiencies or what is not working. It's like the commissioning issues log, you know. It's the tab version of the commissioning issues log. We call it a deficiency report. It's everything that you find that's not working and that needs to be fixed. So that is a very, very important part of your report. What happens is, you know, tab reports are very long. Sometimes they're 300-400 pages. I don't want to have to look through that report to see everything that's not working. I need you to tell me up front that it's not working, so I don't have to do that. So that's the reason that's a requirement. So anyway, testing, adjusting, and balancing is really all about trying to make the engineer's design to work within 5 or 10% of what he specifies. So if he specifies an air handling unit to be 1,000 CFM, then you need to make sure that it's 900 or 1,100 CFM, somewhere in between. It's got to be plus or minus 5 or 10%. Now, normally, it's 10%, okay, normally. Some engineers like 5%, but let me tell you, 5% is very difficult. Your instrumentation has a problem making a 5%, right? So, you know, making 10% is reasonable. When people start wanting you to get into 5%, that's really, really not reasonable. And you have to put a lot of extra money in the job because you're going to have to test and retest and retest to make that 5%, because it's a big deal. 5% is a big deal. Very difficult to make. But what you're doing really is you're verifying that engineer's design. And why that's so very important is because at the end of the job, when a job is completed, it either works or it doesn't work. And every time it doesn't work, the contractor says it's a design problem every time. But the tab report is going to tell you that the design is within 5 or 10% of what's installed. So it's no longer a design problem. If the tab says it's there, it becomes a contractor problem. But, you know, sometimes we can't get there. Sometimes we find out that it really is a design problem, but we find it out early in the beginning of the end of the job. So the best thing to do is find out there's a problem, you know, so you can fix it, not wait till the end when it doesn't work. But what happens so many times with tab is that, testing, you know,
1, 2, 3, testing.
The tab report says it's working fine, and then we find out it's not. So that's a big deal, or a big problem. Okay, come here. Pay attention. I think we got the proverbial lockup now. I think so. Let's see here. Where are you at? I don't like that. Yeah, I think we have the proverbial lockup. So once we determine that the tab is okay and that it's the engineer's thing, it's important to know, like I said earlier, that tab and commissioning have a very close relationship, and that is why they rely on each other for each other to do the job. And theoretically, the commissioning is not even supposed to start until the tab work is substantially complete. Now, it's a great theory, doesn't really work in reality, but it's a great theory. What we try to do is we try to follow them. So if the tab work can start in the chiller plant, you know, then we'll follow them to commission the chiller plant. And then we'll, as they go through the building, we'll try to follow them as we go through. Because really and truly, the tab work needs to be done before we go and try to functionally test anything. But that's what we try to do. So what kind of air systems do we perform tab on? Almost any kind of air system you can see. I mean, air handling units, rooftop systems, air handlers, fan coils, split DX, variable air volumes, exhaust systems, VRF, which I know you know a lot about, mini splits, and also we interface a lot with the building automation system. As far as publications that we use in our work, we use the ASHRAE standard, of course, which is ASHRAE standard 111. It's been around a long, long time, good standard. We also use other publications like the PMP, the Performance Measurement Protocols, Fundamentals of HVAC Controls, and then each one of the tab procedural companies have their own sets of manuals and documents. Here's the national standards from AABC. Here is the tab journal that comes out every month. Here's the NEBB testing protocols, clean room protocols, and that sort of thing. So each one of the tab companies, procedural companies, have their set of manuals that we use to get certified. We take their exam, their test, and then we're certified based on their information. But really and truly, tab work is the same. Even though you may be NEB certified or you're AABC certified or something, or tab certified, really and truly tab work is really all the same. It hasn't changed in 50 years since we've been doing it. And so, the benefits of being a member of AABC versus NEB versus tab, those are just benefits. You have to choose which one you want. But basically, the actual procedures and the testing that you do is exactly the same. So if somebody in Thailand is looking to join an organization, I would tell you that I think all three of them are very good, and you can choose which one you think is very good, but basically we're all the same. The other thing about tab work is it's expensive for a tab company to buy all the equipment that you need to do in order to do your work. Now, I'll just go through a few of the instrumentation that you need to have and that we use every day. But these instruments are very high quality instruments. They're very expensive, and you have to maintain their calibration by a third-party independent lab yearly, and you have to submit those calibration reports with every report that you make. And trust me, people look at those calibration reports. They are very important because, that's what says that your readings are correct. So one of the biggest costs of a tab company is the instrumentation, because if you have X amount of tab technicians, you're going to have X amount of sets of tab equipment and devices and test instruments. And all of those, cost a lot of money, and plus you have to have them calibrated every year, so you have to switch and send the ones and then have somebody use the others. I mean, it is a process, believe me. So the other thing about tab, like I promised you, it is a lot about math and a lot about calculations. So a lot of what we're going to talk about is calculations. Now, I won't go through each and every formula and go by the numbers, but I'm going to give you a general idea and show you how all this works so that you can see it. And then, of course, if you want to pull out your calculator and use it, you're certainly welcome to do that. But I won't do that in front of you, so that's good. So in electricity, we do have to understand all the different kinds of electricity, how it's set up, how it works, and how it functions with equipment. So that's a basic knowledge that a technician has to have, so that when we want to go through and do something, we have to go and test the volts and the amps and the ohms and see how all that works. So when we try to do that, we have to make some measurements and calculations. So one of the common things we do all the time is look at the imbalance or the balance of electrical power on three-phase systems. Because three phases obviously are complicated, and we have to make sure those three phases are in balance, or we have a lot of problems with equipment. Now, some people think this is not important, but I'm telling you, I have a lot of jobs that have electrical problems based on imbalance. And so when you start having those problems, the owner now has to buy a lot of expensive balancing devices, in order to balance the power. So you need to make sure that you do this right and you give the owner good advice so that they don't have to go out and buy very expensive equipment. So if we're looking at a three-phase 230-volt system and the line-to-line voltages are here, what we do is we take that, look at that imbalance, we look at the average there, we plug that in, we got 5 volts, 3 volts, 9 volts. So for the percentage equation, that percentage imbalance is 9 times 100 divided by 235, which is 3.8. Our limit is 2%, so what happens is, since 3.8 is bigger than 2%, you're going to have to go back to the engineer record and say, hey, I got a balance problem, we need to figure it out. Which typically means somebody's got to buy some serious balancing electrical devices to make that happen. But that's one of the electrical stuff. The other very common thing we do is brake horsepower. So if you've got volts and amps in a motor, a three-phase motor, you've got 54 amps, 235 volts with a power factor and efficiency there. You have to calculate what that brake horsepower is, and it's just simple, run the numbers and do the brake horsepower. This happens all the time on every job. You're constantly trying to figure out what the brake horsepower of the motor is in the operational phase versus what the design is. You've got to prove if it's correct per the design, right? Now, the good news for all of us, and the good news for me, is we have a lot of variable frequency drives out there. Thank goodness 10 years ago in the US, almost every job started having variable frequency drives because it makes our life so much easier. So what's good about drives? Many things, but they're very energy efficient, right? Because what you're trying to do is save energy, and if you can do that by reducing 100% to 80% speed, look at the cube root of the speed is 0.51. You have now saved 49% of the energy. That's fantastic. What's good for us is when we have to make an adjustment, we can simply make adjustments there instead of doing what I'm going to show you later, which is changing shifts and changing pulleys and all this other stuff, which is very time consuming. But that's how drives actually work. And as you can see, at 100%, 80% is 49. You go to 70, you're at 66. If you go to 60%, you're at 78% savings, which is amazing, right? It's very amazing. So it's good stuff. Drives are good. What we're seeing more and more and more on the little tiny motors are these ECM motors. And the ECM motors are kind of the same thing, right? Instead of having this big variable frequency drive, you got this little tiny motor with a little controller on it, and that will use this motor, will vary the speed of that motor by a simple varying voltage signal. So ECM motors becoming very popular. I would say in the US, 5 years ago, they were almost never seen. 3 years ago, they started. A year ago, I have them on every job now. Every job, most exhaust fans, any kind of little tiny motor is an ECM motor. So that's great. It's great for the owner. It's good energy savings. And it's great for us because they're easy to adjust. Okay, so now we need to measure air velocity and flows. And what I like to say is TAB is a process, right? Just like eating. You cook, you eat, you clean. You wash, you rinse, you spin, you dry. It's a process. It has steps. So does TAB. TAB has very rigid steps. You gotta follow the steps. And so we're going to go through the steps in detail. Okay, here we go. So here's our step. Number one, you got to locate where you're going to take a measurement. Then you got to measure it. And then you got to calculate it. And that's what we do. So let's get started. If we had a duct, like in this example, and it is comes here, up here, we need to find out where here we're going to take those measurements. So, for example, here, if we did an 18 wide, 12 inch high, we would use our little formula here. We would come up with downstream, 132 inches downstream, 33 upstream, and then this is where we would take our measurement. And we have to do that on every duct that we do. You know, pretty much, once you get experience, you can do it very quickly, but still, it's a lot of time and effort on every measurement you make and every measurement you take, and you take a lot of measurements on a job. So now you've got to measure the pressure, right? So now you're going to choose your instrument of choice. Typically, we choose some sort of a pitot tube, and we start looking for what we're going to do. If it's a round duct, then we have a pattern for round duct. If it's a rectangular duct, then we make a pattern for a rectangular duct. And the way that works for a rectangular duct is we go with a drill and we drill the holes. We just drill holes in a duct, right? And that's for the traverse. Then we take our little instrument here, and then we're going to go in these holes. We're going to put this instrument in those holes, and we're going to read what we're going to read. So here's a rectangular duct example, right? So here we get started. I'm going to go through 5 different processes. I made my holes, right? Just like I showed you, I made my holes. Now I'm going to start at the A hole, right? And I'm going to start taking velocity readings in and out of that hole. I'm going to do it by putting my probe in there. And it has little graduated steps there. You stick it in here, you take a measurement, then you stick it in here, you make a measurement, stick it here, make a measurement, stick it here, make a measurement, in, and you're taking measurements as you go along, right? Pretty soon, you've got your B hole, your C hole, your D hole, you got all those things. You're doing it every time, right? Every time. Here you go. Do the same thing for C, D, E, and F, right? Same thing. Here you go. Now, you take all those readings, here they are, and you average them. Now, when you use a tab automatic computer, which is what most companies have, it does it automatically, right? You don't have to sit there with a calculator and make these things. But if you don't have that and you have a simple little pitot tube and that's what you're doing, I mean, you're going to make all these measurements, you're going to write them down, and you're going to take the average. And then once you have the average, which is your average velocity in feet per minute, and you've got this duct, 36 by 24, which is 6 square feet, you then simply take your formula, right? That CFM is area times velocity. You take your 6 square foot area times your 2518 feet per minute velocity, and boom, there's your CFM, 15,111. That's a typical rectangular duct, and we do that a lot in rectangular ducts, depending on how big the job is, but it just goes over and over and over again. And that's how we measure a rectangular duct. But there's many other duct sizes, there's many other duct configurations, right? There's rectangular, there's round, there's ovals, and I'm going to show you an example for the rounds, and then we'll go through the ovals, right? But just for you to know, you have to, understand how all this works, and that's what you have to do. And this is for the tab technician. He is the person out in the field with all this instrumentation, and he's having to do this time and time and time again. Like I said, a tab technician does a lot of hard work. This is a lot of hard work. It's not easy. So let's look at the round, right? I showed you the little round configuration there where you're going to drill your holes this way and this way. And if the round duct is larger than 10 inch, then you're going to do 20 velocity readings. And if it's smaller, then you're only going to do 12. So you're either going to do 20 but you're at least going to do 12, right? So we'll do an example here where you have a 20-inch round duct. So it's 20 inches, so now you need your 20 readings. So you do your little, your little thing there, and you start taking your first set of measurements with your pitot tube. And then like we did before, we go and we do the second set. And then when we get all of our 20 readings done, right, we got to average them together just like we did before, and we come up with the average velocity in feet per minute in that round duct. And then simply, again, it's the same old formula, is area times velocity, but since you're a circle now, you're using pi r squared. So you take your information, you get your area, you got your velocity, you take the velocity times the square foot area, boom, you got your 7390 CFM. Simple, simple, but you're doing this over and over and over again. So that's on a simple round duct. Now, oval ducts are more complicated because an oval duct is kind of a square duct, and then it's kind of a circle duct, right? But what we try to do to simplify things is we look at two different examples. If it's kind of a really wide oval where the width is greater than or equal to the diameter of the semicircle, then we traverse everything like it's a rectangle, right? We do it just like a rectangle. But if it's one of these fat ovals, like this one, then we end up traversing it like a circle. So that's the difference, right? And you just have to figure out what the size and the ratio is, and then you can go from there. So let's start with an oval duct, a long oval. So because it's a long oval like this, we're going to traverse it like a rectangle. So again, we start by taking our velocity readings, just like we did in a regular rectangular duct, and we go through those. We insert our pitot tube, and we do more on the B's, and all the rest of the C's and everything like that, just like we did before. And then you have your duct diameter, your duct area there, 36 by 24, plus the two 12-inch semi-rounds. So then you figure out what your area is in square foot there. You use a pi r squared there, get the semicircle, and you come up with 9.1 square feet. And then you simply take all those readings, average them like you did before, come back in, do the two semicircles, right? Just like you're doing a rectangle, you got to take those measurements again, just like you did before. Take the other ones on the other side, take them all. Now you've come up with your average velocity and everything like that, and then you simply take those calculations, your area, your velocity, do the math, and you come up with a CFM. And that's the elongated oval. Now you want to go to the little fat oval, and you're going to traverse that like a circle, right? Because you're going to do the bop-bop and the bop-bop. So again, you take your information, you start with your traverse, you traverse it that way, because you're doing the circle one, right? Boom, boom. Simple, simple. Got your velocity, got your area, times that, come up with 10,000 CFM. And that's how you do the fat oval. Now, I mean, it's like never ends, right? Every time you get a different size duct, you got a different size process, and you got to figure it out. And, you have to use your procedural standards from the NEB, ABC, or TAB, or whatever. They'll tell you, how you're going to do each different duct and what that kind of sample. But again, the TAB technician is in the field doing all this work on ladders most of the time. So, it's really hard work, and frankly, it's a young person's job, okay? It's very much a young person's job. Because you know how working on ladders can be. That's no fun. So what I like to say is that the airside tab work is very challenging for most technicians. And usually what we do is we have a tab technician that's certified, but we always put like a helper with them. We always put a helper because it's such hard work to do by yourself, and you really need somebody helping you haul around the ladders and hold the hood and do the pitot readings and this, that, and the other. You really need to have a helper, at least one, right? Because, man, if you're doing this all day, 8 hours a day, I mean, you're going to be very tired. So at least having a helper gets you, to do real productive work for the 8 hours that you're typically going to be on that job. So now you have all your measurements, you have your CFMs, everything's working fine. And of course, if you're here in Bangkok or you're here in my town of Tampa, we're basically sea level, right? We're not very high. So we don't really worry about density corrections. But if you're in an area that needs density corrections for CFMs, if you're in Denver, Colorado, or you're in Bogota, Colombia, now you've got to look at 7,000, 8,000 foot of height. So now every time you do a calculation, you have to end up making a correction for the density. So yeah, the formula is really simple, but again, you got to sit there and you got to do that for every time you make a calculation. So it becomes, a little more difficult for those locations. But we do have rules of thumb, right? So it's about 2% for each 1,000 feet above sea level and about 1% for each 10 degrees above 70 degrees. Now you would have a little tiny correction for heat, right? Because you guys are typically probably like 85 or 90 degrees a lot of the time. So you might have a little bit of correction for that, 1%, 2%. It's not that much. So, but it is what it is. I want to introduce to you, which you will see a lot more times, is these fan laws. And we all memorize these fan laws, and that's how we get through the tab process. But basically, what it's telling you is CFM and RPM, speeds and flows are basically directly proportional to each other. But then when you graduate to pressures, then your pressures end up being squares, right? So you're squaring that relationship between speed and CFM. And now when you get to brake horsepower, now you're cubing those relationships between those kind of things. So I'll show you that as we go along, but that's basically how we make calculations we go from one parameter to the next. So here's an example that we would use the fan laws to transfer from a brake horsepower to a density. So if this fan is operating at 5,000 CFM and 4.2 brake horsepower, the density of the air is 0.062. Find the new horsepower if these standard conditions apply. So what you're doing is you're changing the density, right? And you want to know what's going on with the brake horsepower. Again, you use your simple formula and you go from 4.2 to 5.1. So the density increased, therefore the brake horsepower increased. These are calculations or word problems that you will have on every job, because people will come up to you and say, well, what if I did this, or what if I did that? Well, you just have to run the formula, and so you have an answer for every time they ask you that question. What we deal with a lot in airside tab work is duct leakage. So it's great to run the ducts from the air handling unit out to all the grills, but what happens if the duct leaks, right? If you're leaving the air handling unit with 1,000 CFM and you leak 500, then you only have 500 available for you at the grills. But that's not a good thing, right? It's not a good thing. And our codes don't require that. I'll show you in a minute that we have very low leakage codes. So obviously the mechanical contractor has to seal those ducts, and then as a tab professional, we have to test those ducts to make sure of what that leakage is. And so when we do that, we use ASHRAE standards, a new standard that just came out in 2018, which takes duct testing to a new level by actually specifying the methods of test that we have to use to determine that leakage. Now, we've been using these similar methods for years because our own tab company standards tell us exactly what we need to do. But when you're measuring that duct leakage, you need to do it by some standard of care, right? So we do that. Now, these are some examples of duct pressurization machines. I mean, duct pressure testing is not rocket science. You're taking a length of duct and you're sealing it on both ends. You're putting this machine into it, you're blowing air into it, and you're measuring the leakage. It's as simple as that. But you have to do it for, depends on how many feet of duct that the engineer specifies. Sometimes they specify all of it, sometimes they only specify, 25 or 30% of it, but you have to do it and you have to document it. So these are just some of the setups for that. You can see that we're piping the machine into the duct, which goes out here, and then we measure that duct testing as it goes along. Obviously, we document it on a test summary sheet here, and then finally, this is a typical standard of care for how much duct leakage we're going to allow. In very small systems, it's basically 2%, right? When you get into the much bigger systems or high pressure, then you get into the 1%, but generally speaking, 1 to 2% leakage. So that's not much. It's not much. And so when you find the ducts leaking 5% and 10%, that's terrible, and you have to go and seal it until you can at least make this 1 or 2% level. It takes a lot of work by the mechanical contractor to seal the duct. And many times, if you have external wrap insulation, by the time we get there, if they've already wrapped the duct, then we don't know it's sealed. So when we test it, we'll find out. We'll find out, because if they didn't seal it, if you don't seal duct, it'll leak 40% easy. Very easy. So, really quick if they didn't seal it. We have a name for that. We call it Pookie. Have you guys ever heard of Pookie? Pookie is the duct sealant. It's like a gooey goop that you put on you brush on the ducts and it seals. It dries hard and it seals the duct. But that's a hard job, because you got to get up on a ladder or a lift and you got to go do all the duct, and it's a very hard and long process. So yeah, this duct testing is very, very important, because when you come down at the end of the job and that engineer specifies 1,000 CFM and you start testing the grills and you're getting 500, you know you're in trouble, and you know that nobody sealed that duct. The other thing that's becoming incredibly popular is building leakage, right? Testing the building for leakage. Now, I actually had to do this, it's 2006, so I actually had to do this like 15 years ago. It wasn't common back then. It was a government building, and they were the first to specify that buildings could not leak by a certain percentage. And I actually had to pressure test a huge building, and there's no technology available to do it back then, so we had to use the actual air handling systems to actually blow up the building, but we did it. But now, the U.S. Army Corps of Engineers, they have a lot of good information on building leakage. ASHRAE has some, of course, but the Army Corps has a lot of really good free information on how to do air leakage in buildings. So you should check it out. But basically, there are a lot of people that have the information. ASHRAE does. ASTM has some methods and things like that. It's fine. The concept is pretty simple. You need to seal the building, and then you need to be able to pressurize the building and depressurize the building, and then test how much airflow you're losing. It's just like pressure testing a duct. It's no different. You're still pressuring the building like you would pressurize a duct, and then you're measuring the air leakage that you're losing when you do that. So this is typical building, looking at buildings. This is another example of a building. These are blower doors. Blower doors are the devices that we use in small buildings. This is actually the door that we took off, and you put the blower door in its place. And obviously it has a big fan there and some instrumentation. And you put this blower door on the building, and then you run the fan either this way or that way, and you can either pressurize or depressurize the building. Really interesting process. Very interesting doing it. There's a typical blower door there, and another blower door there. This is a job that we did in an Army base where we compared two buildings to the same. So we did put the blower door on there. Then you have to seal all the windows, seal all the exterior. You have to seal all the grills in the building, because when you blow up the building, you want to see how much is leaking through the infrastructure of the building, not the air vents and the air handlers and all that stuff. All of that has to be sealed. And then we took this building 1540A, which was the retrofit building, compared it to the building next door, 1540 B. The standard we were using at the time is we need to make sure that the air leakage is less than 0.25 CFM per square foot when we test it at a pressure of 0.3 inches water column or 75 pascals. That's typically the standard back then. This was like 15 years ago. What we did is we compared the two. We obviously failed many times, many times, and eventually we did actually pass just by a little tiny bit at 0.24. And of course the building next door that we were comparing to, it was terrible. It's terrible. These buildings were built like 20 years ago, and they were just leaking like crazy. So, I mean, that was the point of that particular test, but we do them all the time. It's very common to do this now, and the leakage rates are changing. Like when we did it, the standard rate was 0.25 CFM per square foot, but now it goes anywhere from 0.4, which is higher, to 0.15, depending on the location and jurisdiction. Just depends on who is specifying it, whether it's the government or the engineer of record or the architect or whatever. That number changes a lot now. And when it changes, it's difficult. I mean, it's difficult to get 0.25. If you try to go down to 0.15, that's really crazy. I mean, that is absolutely crazy. That is a tight building. But it happens. Now, what's really strange is in my state of Florida, it's now code that the contractor has to blower door pressure test every residential house, every one that's built, every one. So every house I built or I bought in the last 10 years has to have a blower door pressure test on it. And it has to pass, right? I mean, that's wild for residential buildings, but they're really taking it very seriously, because obviously if the building leaks, all of your cooling or your heating or whatever is going out the window or going out the door or whatever is going. So it makes good sense for energy efficiency to make sure that the building is tight and doesn't leak, right? I mean, it's really good. But when you try to apply that to commercial buildings, that's when it comes really difficult, because houses are houses, you know, 3,000, 4,000, 5,000 square foot. But when you're talking about commercial buildings, now you're talking about a lot of preparation, a lot of thinking, and a lot of time to pressure test that commercial building. It's coming. It's coming. If you look at ASHRAE standard 90.1, you'll see that 90.1 2019 is on the verge of specifying it for commercial buildings. In the 2019 90.1, it's voluntary. But when they revise 90.1, which they do about every 3 to 5 years, I think you're going to see them try to bring in that pressurization. It's a big deal and a big cost. I think that everybody has to be very aware at how much it's going to cost you to pressure test a building. So I know that in Thailand you may not be doing pressure tests on buildings yet, but it's a real cost. I'm not saying it's a bad idea. I'm saying it's a great idea, but the marketplace really has to be ready for that. because it's not something you're going to prepare for overnight. You're going to need years and years of prep and practice in order to get it right. So that's just what I think. So the other thing we do a lot is measure the rotational speeds of any kind of shaft or motor or anything like that. So we have specialized instrumentation that we have to buy in order to do that, or we can use fan motor shifts. So I'll show you how to do that in both ways. So here we go. We have a motor shiv right there. This is the shiv, right? This is the shiv. This is how you adjust it. And what you're doing is you're adjusting this space here so that this fan belt either rides high or rides low, and obviously where it ends up in the groove changes the speed of that rotation, right? So when we have to make adjustments to speeds or flows using shivs, it's a big process, it's a heavy process, and very difficult to do. But here we go back with the fan laws. You're going to see these fan laws all the time because we use them all the time. Here's what we're trying to do here. We're trying to take a fan that's running at 750 RPM and 10,000 CFM, and it's changed to 795. So what's the new flow? Obviously, we use our fan law, do the math, and it goes from 10,000 to 10,006. So that's one example. Now we have the fan and pulley, right? We have the motor down here, fan and pulley up there, and now we want to make some ideas here. So this fan is delivering 1,500 CFM with a shiv of 13.6, but we want to reduce it. So how do we do that? We change the shiv out, we do the math here, and we can change it to a 4.25 inch shiv in order to get this reduction there. So the rule of thumb that we use in the business is if we increase the size of the motor shiv, it increases the fan speed. Decreasing it obviously is the opposite. A lot of times we change shivs on motors, a lot of times we change shivs on fans. So if you do the fan, it's obviously a different process. So here we're trying to take that to a different speed, increasing the flow to 18,000. So we solve for the new RPM, and then we take that diameter of the shiv, put it in our formula, and then we come up with a 9.4 inch shiv as opposed to the original. After you change the shivs, whether you do it on a motor or a fan, guess what? Now you've got a fan belt problem. Maybe you need to change the fan belt. So we have a formula for that, as I'm sure you might have guessed. So we take all these measurements here, we put it in our formula, and boom, now we need a 43.9 inch belt where we had a 43 inch before, and sometimes you have to change the belt, sometimes you don't. But my point is, man, this is a lot of work and a lot of time. Tab professionals, tab technicians do an incredible amount of work. I think they're great. I really do. I think they're really fantastic. So, man, and the reason I kept telling you that variable frequency drives and ECM motors are a blessing, a real blessing, is because once you have a VFD or an ECM motors, you don't have to worry about all this shiv stuff anymore. You can just vary it by the speed of the drive in 2 minutes instead of doing this for 2 hours, because I'm telling you, by the time you go in there and you change shivs and you adjust it, you take new measurements, you do it again and again and again until you get within 5 or 10%. I mean, you're there for 2 or 3 hours just on one motor. So very time consuming. Variable frequency drives and EC motors, they are a blessing to a tab technician. So fans. We love fans and we love equations with fans. We got an equation for everything you can imagine, right? And we use them all the time. Again, I love to remind you about all of these fantastic fan laws and how often we use those. So here we go again. What happens if I want to change the relationship between the speed and the flow? If the fan operates at a certain speed, at a certain flow, and now I want to change it, I can certainly use my RPM and CFM formula to figure that out. Similarly, with the next one, if I want to do it the same, at a certain speed and a CFM, I want to find a new CFM. Again, I just use that formula. I know I'm saying this over and over and over again, but that's what TAB is all about. TAB is all about the math and all about the equations. So I'm going to show you more, because when you go from CFM to RPM, that's straight line. When you go to pressures, that's square. And when you go to motor power horsepowers, then you're doing cube. But I just want to show you kind of the same thing, but using the pressure. So now we're dealing with static pressure. So we're operating a certain speed at a pressure, and now we want to go to a different one. So now we have to go to the static pressure RPM relationship to come up with the new inches of water column pressure. Similarly, the same thing. We have a fan operating at a certain flow, at a certain pressure. Now we want to reduce it, find the new static pressure, and here you go. Similarly, we're going to use it for static pressure and density. Again, the fan operates at a flow with a static pressure and an air density. Want to find the new static if the densities increase. Again, you use the formula. I told you I would go through these and show you how much and how often we use these all the time. Here we go with a brake horsepower, which is going to be a cube. It operates at a certain speed, at a certain horsepower. You want to change the speed. Guess what? You're going to change the horsepower. Similarly, a flow at a horsepower, the air volume is increased. Again, you're going to get a horsepower. And that's how it works over and over and over again. We do it on all kinds of fans, in all kinds of questions. You remember getting word problems in school? Well, that's what test and balance is all about. We get a bunch of word problems and we have to figure it out. So I hope that I have convinced you that TAB work is all about the calculations and all about the numbers, because that's what we do all day. Thank goodness most of our equipment is computerized, so we don't really have to go through all this math. We just plug the numbers into the little computer, and we take our measurements and all that, and the computer acquires that and ends up telling us, the end answer that we're looking for. But, when you're first starting out, you have to figure out how that works. And that's what, what gets into a lot of work and a lot of training. So TAB professionals, TAB technicians, and TAB engineers, they really do need to be very technically oriented and pretty much very near to engineers, because whether you're a TAB technician or a TAB engineer, you're dealing with so many formulas and so much stuff. It's really as if they're an engineer in general. So, but we also have fans that operate in parallel and in series. Obviously, in our world of TAB, most of the time everything works in parallel. We don't have a lot that works in series, only every once in a while. So most of our work is in parallel, but sometimes we do have series, and of course, if you have sometimes, then we have to be able to account for that. So let's look at some popular fan types. A lot of them out there, centrifugals, axials. Here's some samples of them. These are samples of parallel fans and air handling units that are being operated by VFDs. These are different brand air handlers, but as you can see, some air handler manufacturers are doing 4, 8, 12 fans in parallel. I mean, it's just what's going on. Now, what happens is these little motors are much smaller, and these motors are obviously bigger, but manufacturers are doing a lot of these fans in parallel because, if you only have one fan and it breaks, guess what? You get no air, right? So a lot of people are getting smart and go, hey, if I have 2 fans or 4 or 6 or whatever, if a couple of them break, it's not a big deal. I don't lose the whole building, right? I only lose it until I repair it. So it's really a good idea. I mean, it's really a good idea what they're doing. So that's fine. So, but the way they operate, if you're operating in parallel, the CFMs or the flows add, the pressures remain the same. So you can see here that the flows add, but the pressure is going to stay the same. So what happens is, if you take 2 fans, both operating at 20,000 CFM and 2 inches of water column, and you combine them, What you're going to do in parallel is you're going to go 20 plus 20 equals 40. So you're now going to get 40,000 CFM, but that pressure is going to stay the same. And that's operating in parallel. That's what we do the most of in HVAC&R. We very rarely see fans operating in series. But if we ever do, we do have formula for that. So if they're operating in series, the opposite happens. The pressure adds, the CFM remains the same. So you can see here that the CFM remains the same, right? But the pressures are adding up. So if we had used the same example, two fans each having 20,000 CFM operating at 2 inches, if you run them in series, now you have the same 20,000 CFM, but now you have 2 times 2 or 4 inches of pressure. So that's basically, how those fans work in parallel. Of course, we have curves. If we ever need to know how things are operating, we look at the fan curves, and each fan curve will tell us how that fan operates. As far as air distribution, when you install the ductwork, there's a lot of air distribution moving parts out there, right? And we're going to go through just a few of them. This is a typical layout of ducts, and you're going to see all kinds of balancing dampers here. This is how we balance the air coming out of these grills. We do that by these little balancing dampers, and they're very simple. There's a lot of different kinds, but they all pretty much are the same, right? They're just a little damper in the duct with a little handle there that you adjust open and closed, okay? Very simple, and they work very well. This is another example. As you can see, this just moves up and down based on where that position is. And then as a test and balance professional makes his calculations, then he can adjust that damper in the duct and then lock it. It has like a little lock nut there, and you can just lock it into place, and then you balance that duct. So now we're going to practice what we do when we first come to a job and we're getting ready to actually do the actual air balancing. Very important that you have to go around and you have to prepare. You have to review the contract, and we already told you earlier that you need to read the specification. That's going to tell you all of the stuff that you have to do, but you also have to walk around and see how the job looks. You've got to make the site inspections, and you have to make sure that all of the units have been started up properly, the air handlers, the exhaust fans, all of that. The mechanical contractor starts those up and makes sure they're run. Before you get there, you as a tab professional are not supposed to be starting up equipment. So you need to walk around, find out that everything's running, and if it's not, you have to come and tell the contractor that they need to go start it up and get it going. Do not skip the site inspections or the walkthrough. It's the same as commissioning. When the contractor calls you and tells you they're ready for the tab work, 9 times out of 10, they're not ready for the tab work. You've got to go there, walk the job, and tell them all the things and all the places where they're not ready. You do not want to drag all your equipment there and get there to find out that they're not ready and you can't do anything, and then you need to go back home. You need to go there and do the inspection, walk around, see what's going on before you go there. It's very important. Otherwise, you will waste a lot of your time and money going to jobs that are not ready. So this is just kind of telling you basically what you're going to look for. You're going to check the rotations of the fan, make sure the filters are all clean, everything is working properly. You go around and you look at that and you make sure. You're going to start your basic tab procedures on the air side. You're going to look very simply at the air handling systems, which typically are supply going to a room. You've got outside air or ventilation coming in. You've got a return coming back around, and then you have some sort of an exhaust. Obviously, you need to check it, because if any one of those aren't working, you're wasting your time doing anything. You cannot test, adjust, and balance a system that any part is not working. So if for some reason the exhaust fan's broke or the outside air damper doesn't work, you need to walk away, because whatever you do is a complete waste of your time, and it will be wrong if you think that you can test half of it and then come and test the other half later. That's not the way it works, okay? You just can't do that. So you go and you look at it. For example, the airflow monitors, which is very key to ventilation. You need to make sure that all those airflow monitors are installed and working. We do that simply by filling out a sheet, an air monitoring station data sheet, and we make sure of what the designs are, and then when we're ready to test it, you know, we fill in the test. But the thing of it is, airflow monitors are used frequently now in HVAC and our systems because there is such a demand to meet ASHRAE standard 62, which is a ventilation standard. That standard has grown in importance through the years, and now it's gotten to a point now where we're actually doing demand control ventilation. So now we're operating the ventilation at different levels for different levels of carbon dioxide in the space. And so understanding how that works and making sure the airflow monitors work is very key to the TAB process. Now, the good news is the last hour of my talk this afternoon is everything you always want to know about airflow monitors and what can go wrong, so I won't spend a lot of time on airflow monitors here. But airflow monitors are so very important. They must be installed in the right place, and they must be working, and we'll talk about that a lot. So what you do is you have to sit there and you draw out the air handler, how it looks, and then you start looking at the general process of where you're going to start. So make sure all the bouncing dampers that we told you about, they all have to be open. Make sure they're all open. The contractor knows when they install the ductwork that they know they're supposed to leave those open. They don't always do that, but they're supposed to do that. So make sure that those are all open. Make sure that you've done all your preliminary tests to see where you're starting at, and then making sure that your traverses are all going to work out within 10%. So here we go, right? Here we go. We're going to look at the supply, the outside air, and the return, and that's what you got. So you're going to start at the air handling unit, because if you don't have it at the air handling unit, you're wasting your time going out in space. Because if you don't have it here, you're not going to have it out there. So that's why it's important to start where we're starting. So here we go. We're going to start at the closest branch, the highest flow. Okay, so here we go. We got a 500 and we got a 710. Guess where we're going to start? The 710, right? So we go to the 710 and we say, hey, 710, the design's 660, but you're at 710. So what do I do now? Aha, I'm going to show you those equations that you love so much, right? So here we go. We're going to go up there. We're going to make some measurements, see where we're at. Guess what? What we're looking for is 660, but we got 710. So what are we going to do? We're going to use our favorite pressure formula there to say, hey, at this point, we need to take the ratio of the air, what we want and what we got, and now it comes up to 1.6. Guess what? We need to balance that junction right there at 1.6 inches. And if we do that, then we got our air. That's when these formulas come into play, is because that's exactly what we're doing. We're trying to figure out what we got here. So we know we got 710, we want 660. So we just do the math, and then we say 1.6 here, boom. We do the 1.6, and we're good to go. We bounce that damper, now we got 660. Now we keep going down the road, man. We just keep going down, 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 and do all the rest of them, which is a lot of them, right? So now you're there, right? Now you want to start doing the grills and the terminals that are out in the space. So again, we get ready for our pitot tubes. We get ready to start on the return and exhaust, and it's a similar thing. Here we are in the return. We're going to pick the largest one, right? The 500. That's what we're going to go to first. And as soon as we get that 500, we're going to go to the 200 and then the 100. Now we balance the return. We kind of know what we got coming in, and similar then with the outside air. Now, a lot of jobs these days have variable air volume boxes. Do you use a lot of VAV boxes here? I don't know. Do you see them a lot or no? We use them, I mean, almost everywhere, because it's great, because they go from a low CFM to a high CFM, depend on the temperature of the room. So it's really forgiving, very forgiving for a design engineer. He can have a lot of leadway to get the temperature he wants in the room using different flows. So we have a lot of VAV boxes, and we do a lot of this. We do a lot of that. So for example, here's 3 of them. And what we do is we look at the plans and the specs and look at the submittals, and it's going to tell us all these boxes. It's going to tell us what the minimum CFM is, what the maximum is, and then what we want as far as heat. So that's what we're going to balance to in VAV boxes. So then what we simply do is we go to the thermostat, and we're looking to set the maximum flow. So let's just say the maximum flow is 1,000 CFM. So we go to the thermostat, we set up for maximum CFM. We're trying to get 1,000 CFM out of that grill, so there we go. We're going to put the hood up there. We're going to measure what we measure. Then we're going back to the thermostat and set it up. Next thing you do is the minimum, same process. You go to the thermostat, go to the grill, and there you go. And then you have your maximum and the minimum. And then next thing you're going to do, if you have heat or reheat in the VAV box, then you have to set the reheat CFMs. Typically, reheat is about 1/2 of the maximum. So it depends. I mean, a lot of engineers use a lot of rule of thumbs, 100 CFM per kW of heat or whatever, but generally speaking, it's half of the max. So you go to that box, and you look at it, and you have to modulate the air down to that 50% level, and then simply do the same thing as you did before. Go to the thermostat, set it, and then you're good. And then the VAV box is basically balanced. And so one of the arguments in using VAV boxes between the tab professional and the control guy is that once you set that VAV box, then there is what we call a K factor. It's now programmed into that box. It's a factor that that box uses. And so what the tab professional likes to do is they like to write down that number, which is typically some fractional number of 1. So it could be 0.3, 0.6, 0.85, whatever. But what happens is, if you ever have to change out the controller or change out the box, you can go back and use that K factor in your new box, and so you don't have to go and tab this box again. So it's very valuable to get that K factor. The argument we get from the control BAS people is, oh, well, they don't like giving it to you or whatever. So there's an argument in the industry right now. We definitely need the K factor so the owner can have the benefit of that number, so the owner doesn't have to go pay someone to tab that box again when it breaks. And it will break someday. And so it's great to have that information. So as a tab professional and a commissioning professional, we try to make sure that we get that K factor put into the report so that it's forever there in the VAV box data sheet report that the owner gets at the end of the project. The other thing we do on buildings is we have a lot of chill water systems, we have a lot of large DX systems, but we also have a lot of small refrigeration systems. The tab work on small refrigeration systems is really pretty small because there's not a lot that you can adjust on it, but it's important to document it and make sure that we have everything listed on a piece of paper so that the owner has that in the future when they want to modify the equipment, reuse it, replace it, whatever. So I'll just show you that, we have any number of small direct expansion DX refrigeration devices that we use. We typically will do a lot of documentation on the fan and evaporator as far as how that works, and then on the condenser side, we note a lot of that. Usually it's very simple and easy, but we just make sure that we document it for the report. It's really easy to do, and we like to put that in the report in general. So what we've done is we've talked a lot about a lot of different systems. We test and balance on the air side a lot of these different systems. There are a lot of other systems that we didn't cover, but in general, this is the general idea on what we do as far as the tap water stuff. I will end telling you that we do not normally do noise and vibration tests. Noise and vibration tests is very much a specialty in the tab industry. It requires a whole nother level degree of instrumentation and expertise. So it's not done on a regular basis on a normal project unless somebody starts noticing that there's a bunch of noise coming from somewhere. So as long as, like in this room, we're okay, we're not hearing any crazy noises, we're not going to spend $1,000 testing the sound and vibration in this room. But if we heard this horrible noise or things like that, then yeah, obviously we would. But normally we do not do that on a normal job. We just leave it alone and make sure and think it's okay. Now, normally on HVAC&R systems in normal buildings like classrooms or schools or hospitals or whatever, we just do the normal everyday units. But sometimes, like in commissioning, we have to go and do specialty rooms, like in hospital rooms, data centers and laboratories, pharma, clean rooms, that sort of thing. We talked about this as far as the commissioning, but most of the commissioning work in a clean room is done by the tab professional. And so I just want to go through briefly what that tab professional has to do. The tab professional is doing all of this. The commissioning person really only does like sound and vibration sometimes, and they do the airborne particles. But all the rest of this is typically done by a tab professional when you're doing clean rooms, because it's really all about the airflow and the pressures and everything like that. So they go through and spend a tremendous amount of time doing their tab work in these rooms. And many times the working conditions are pretty crazy. But just like commissioning, they all have to gown up because you got to go in the clean room. But a lot of clean rooms are very high ceilings. And a lot of the work you have to do is actually in these high ceilings, because in a clean room you have your normal unit feeding the clean room, but then in the ceiling spaces you have a lot of HEPA or extra special filtration, and then the tab professional has to get up in those ceilings and measure what's going on with those HEPA filters. So it's a lot bigger deal, when you're going and doing that. So the test instruments are pretty sophisticated. You obviously always have to be gowned up, but again, the tab person is doing most of that hard work, and they're producing the report. So just, in those kind of rooms, it's really mostly done by the tab professional. So what we did is we spent the last 45 minutes to an hour on the air side. And that's the air side. And we're going to end the air side now, and we're going to take a little break. But I want to make sure that we answer any questions that you might have on the air side. What we're going to do in the next hour is we're going to go to the water side. And that's, it's kind of like the same with water, but it's a little more heavy, you see. So let me ask if anybody has any questions on the tab work on the air side. Please raise your hand and we'll answer the questions now. and then we'll take a coffee break and come back and do the water side.
Yeah, I have a very basic question concerning measuring point and number of it. I see this figure and this photo. You have three arrow.
Yeah.
What is the meaning of three arrow, and how do you calculate? How do you measure this kind?
Yeah,
Please.
what happens is this, yeah. So what they're doing is they're taking this probe and they're putting it in a duct. And let me see if I don't have a probe thing. So anyway, they're sticking the probe in the duct in this first hole. See this, that's A, B, C, let's call that C hole. So in the C hole. So in order to go in the duct at different heights, they have to push that rod in at those different places. And that gives you all the different readings inside the duct. Because, you know, it's a square duct, but you start here on this end, you go in a little bit more and you get that flow, go in a little bit more, you get that flow, go in a little more, you get that flow. So you have to get the velocities at all the different locations inside that duct. And that's why you have to do that.
Just measure one time.
No, well, no, you measure one time, but you measure one time here, then you push it in, you measure again, push it there, measure it again, and again, and again. Then you go to the next hole, do the same thing, over and over and over again. Because the velocity inside a duct is different depending upon where you're at. So unfortunately, you have to take a lot of measurements in order to be accurate. That's just the way it is.
You measure only one number, but different locations.
Different locations, exactly. And again, like in that example, you've got like 50 or 48 locations you end up with. So you have to average those 48 locations to get your average velocity. Thank you.
For the tall buildings, we encounter the pressure distribution along the height of the buildings. How do you perform the tap for the whole building seal, leakage?
Yeah, tall buildings are a specialty. Tall buildings are very much a specialty. Once you get above 5 stories, 6 stories, then you start getting into stack effect. And that's a big deal. That's a complete specialty in itself. And the tab manual will help us with that, but it's not a part of this course because it's just not normal. Just not normal. But yeah, I mean, there are a lot of specialty engineers that only do tall buildings. That's all they do because it's so different and so different. Questions on airside? Yes, sir.
In the U.S., when you compare to ductwork installation and for testing, commissioning for the ductwork, what is the cost of the labor compared to the duct installation cost? What is how many percentage?
Well, the cost to do the testing, it's probably only like 1 or 2%, maybe 1 or 2%. Not much, not much. You know, but still 1 or 2% can be a lot of money if it's a big job. 1 or 2% would be big, but that's it. That's about what the cost is as far as the percentage of the cost of installing the ductwork and including that. Yes. Questions? Now I think this setup is we're supposed to continue on in this session, and I think we have a coffee break in another hour, I believe. Isn't that correct? So we won't be taking a break, but I wanted to take a break on air versus water because when we get into water, it's going to be a lot different, and we'll talk about different ideas. But believe me, air and water is pretty much the same. It's just, you know, we use different formulas and different things in order to do that. Okay. Water tab, right? Different, but the same. So we use a lot of the same principles and a lot of the own equations. What's different, obviously, that they're both fluids. Air and water are the same thing, but of course, they differ by their density, right? Air weighs 0.08 pounds mass per cubic foot. Water is 8.33. So as you can see, there's an order of magnitude difference there. That's a big difference in the equipment and the scale of the equipment, the cost of the equipment, and the ability for a person to work by themselves doing it. We almost always have two people working on water side because the sheer weight of the equipment is very difficult to handle. So that's what we do on the water side. As you'll see, instead of fan laws, now we got pump laws. But as you can see, it's the same. The GPM and the speed are still proportional. When you get into the head or the pressure, that's a square. And again, when you get into brake horsepowers, you're getting into the cubes, right? So we do a lot of different water systems. This is just some ideas of some systems we do. That was a chiller. This is a cooling tower. These are just photos of systems that are included in much of the water side stuff that we do. We also have to calibrate a lot of the metering devices, such as BTU energy meters, water pressure meters, water flow, water differential, that sort of thing, and we use a lot of different gauges to do that. Flow meter calibration is hugely important. The tab professional always helps the controls or BAS contractor to make sure that what they are saying they're reading is actually what we're reading. So that's a lot of what we do and a lot of the instrumentation we use on the water side. Again, very, very similar to water, just much, much heavier. As we told you in the air side, we use a lot of the same equations on the water side. So here is an example. If we have a chiller that's rated at 30 GPM at 4.6 of pressure drop, the entering pressure drop is measured at 28 feet and the leaving pressure is 25.5. Find that actual flow rate, and again, you use your formulas in order to do that, GPM and then the pressures, and you come up with 22 GPM. Just another example of how we use the formulas. We use a lot of formulas when we're trying to calculate what's going on with valves, control valves. And the famous formula that we use for control valves is GPM is equal to the CV, the square root of the delta P. So anytime we have a control valve and we're looking to find out what the flows are, we can simply use the CV of that valve and the square root of the delta P in order to come up with that GPM anytime we want it. And we do that in many, many different kinds of word problems or questions that come up on any jobs. This is very common to try to figure out what GPMs are going through control valves on a job. Water side, just like the air side uses fans to move the air, we use pumps to move the water. There's a lot of different kinds of pumps. These are just some examples of the pump and the internal layouts of the pump, the kind of impellers that we use to push the water. Obviously, this is the impeller that pushes the water. It can come in a closed, semi-closed, or an open fashion. Depends on your application. The engineer of record will work a lot with the pump manufacturers and the pump vendors in order to figure out what the best one is for their particular desire, right? Here's some very common HVAC pump characteristics shown here. Bad things can happen with pumps if you don't design them or install them correctly. One of the worst things can happen is cavitation. Cavitation happens and then you get a lot of bad action, right? So cavitation is a condition when inside the pump, the internal pressure falls below the operating vapor pressure of the fluid, causing that liquid to boil or vaporize. That water pump then is trying to push steam or water vapor, through a pump, and it doesn't work well, right? Doesn't work well. It gets very noisy, and if you don't fix it right away, it'll actually damage the pump and damage the systems you're working with. So we watch out for that a lot, and we make sure that we document that the pump is installed correctly at the right heights and everything like that, so that we don't have the issue of cavitation. Again, we use the same pump laws that we have in the past, same as the fan laws, just a little bit different, right? So when we're trying to calculate the horsepower of the water going in the system, there is a general theoretical water horsepower, but we can't use that because pumps are not 100% efficient. So what we do use is we use a brake horsepower equation that has all the built-in efficiency factors to make sure that we calculate the brake horsepower of the pump that's operating in the system. So for example, if we were looking for the brake horsepower of a pump operating at 142 feet of head at 980 GPM with an efficiency of 0.74, we would use our formula and we would come out with a brake horsepower of 47.5. Again, we have to check the brake horsepower of the design versus what the brake horsepower of the actual operating conditions are. So yes, we use these equations a lot just to double check what's going on in the system and make sure that when we document it, we can tell the engineer of record that yes, his design pump is operating within the design parameters that he specified. This is another pump law, right? Same kind of thing. We're looking at a flow of 100 GPM, the speed here. We're looking for a new GPM. I told you that I would show you how the formulas work, but I won't go through all the numbers with you. You're welcome to do that, but I want to show you that we do actually use these formulas all the time. And that's what TAB is. It's a lot of math and a lot of formulas. So here's another example of using it in head pressure. So you've got a head pressure of 125, your speed is here, now you're looking for a new head, so you take your equation and you come up with a new head. Similarly here, operating at a head here, at a GPM, now you're looking for a new head, again you do the math and you're good. This is an example of how you use brake horsepower in the pump laws. The pump operator's at an RPM at 10 horsepower, you want to find the new horsepower if you raise the speed. Again, you use that formula and you've got it. Similarly here, you got 100 GPM flow at 20 brake horsepower. If you increase the volume to 150, what do you end up with a horsepower? And there's the answer there. Another way we use it is the impeller diameter. The impeller of a pump is the same as the sheave part of the diameter of the sheave. Very similar formula. The pump operates at 20 brake horsepower with an impeller of 10 inches. Find the new brake horsepower, use the formula, and you come up with it right away. Like I told you in the beginning, we use these fan and pump laws all the time in everything we do. And it's just, I know it sounds repetitive, but I just need you to know if you want to get into the TAB business, this is what you're going to do. It's a great business, and it's a lot of fun, and it's very challenging. But you have to find somebody that has the aptitude to use the math and the formulas in order to do it, because they have to enjoy their work because they're going to be doing this work every day. We talked about fans operating in series and parallel. Pumps operate in series and parallel as well. And it's not that much different, right? It's really very much the same. In a parallel operation, which we see most of the time, the GPMs and the brake horsepower add and the heads remain the same. Very similar with the fans, right? So if you took a single pump at 60 GPM at 120 feet of head, 3 brake horsepower is added in the parallel with identical pump operating at 60 and 120, the result would be a total flow of 120 at 120 feet of head, just like it would when we did the parallel fan. The series is very much the same, and it's the same kind of relationship. Now the heads and the brake horsepower add, but the GPMs remain the same. So you started off with 60 GPM, 120 feet of head at 3 brake horsepower. Then you add the 60 and the 120. The result would be a a total flow of 60, which of course is what you had before, but now you've got the adds of the feet of the head and the adds of the brake horsepower. So really, pumps and fans and series and parallel work pretty much the same. And basically, we are almost always using pumps in parallel in HVAC&R. We rarely use pumps in series, very rare. I've only known a couple jobs in my whole life that I've ever seen series pumping. It's very uncommon, right? And of course, anytime you do anything with fans or pumps, you see the resultant series fan curves and the parallel fan curves here. Very common, very similar, right? So here is a simple example of a pumping system and how it typically operates. You'll notice that everything is closed. There is no open. Everything is closed here. So everything is pressurized in how it works. We use closed systems in most chilled water applications and most hot water boilers and things like that. We use open pumping systems for things like cooling towers. The pump will, pump through the condenser, it'll come up, it'll drop the water through the tower, it drops into the basin, and then it's picked up again by the suction and comes back around and things like that. This is an example of an open system, and so we have to be very careful with these open systems, maintaining a certain height here between here and here, because when you start varying the heights between the pump and the water levels and things like that, that's when you get into trouble with getting air into the system, and also you can cause cavitation of that pump. Very simple to get yourself in trouble in an open system. Much more difficult to get in trouble in a closed system. Most closed systems are we say they're very forgiving, very forgiving. The worst thing that happens in a closed system is you get an air leak, and you get air leak in the system, and then you have a really, really upset and mad pump. But in most other cases, closed systems are very forgiving, very forgiving. Again, when you're trying to figure out how a pumping system is supposed to work, and you are doing it from scratch, what you have to do is you have to plot points, right? You have to plot the system curve at different points and then figure out in this system curve where your actually operating point is. So here's a pump curve of the pump, but you don't know how it operates in your system because you're sticking a pump in there. You don't really know how the system operates. So you have to take these measurements and then plot this operating curve to see how it's working at that operating point. This is something that we do a lot, and basically it just confirms that the engineer's design is working properly. Long as we're getting within 5 or 10% of that engineer's design as far as the pressure and flow requirements, then we're good to go. And again, we make the adjustments to get there, so most of the time we get there. We rarely see problems with pumping systems not meeting the specifications. And the good news is, with the new technologies and the variable frequency drives and more technology that I'll show you in a few minutes, our job as a tab professional in the water side is getting much easier and much more much easier to work. So we're getting there. We're making a lot of progress, so to speak. So when you're trying to start the water balancing process, it's the same as you did in the air side. Walking the job, making your inspections and observations is so very important, because people will call you all the time and tell you everything's okay and everything's ready for you, but that doesn't always happen. When, now or after this? How many more minutes? Okay, good, got it. So it's important to make sure that you do your inspections and get that right and do that before you start. Because obviously, if the job's not ready for you, it's not ready for you to start. So we got to make sure we do that. Now, what we're going to do is we're going to make a little stop here because I'm told that the coffee break is here and ready for you. So we're going to take a little break and we'll be back in, 15 minutes to continue on. So 10 minutes? 10-minute coffee break. Good. Well, all right. We'll see you in 10 minutes then. That's good. Buddy. All right. Coffee break. Coffee break. So we were talking about when you're getting ready to do the tab water balancing that you need to go through and do your startup reports, look to make sure everything's been started properly, make sure all the strainers are clean, that everything is ready for you to do your testing, adjusting, and balancing. This is a step that you need to do because, like the air testing, when people tell you they're ready, it doesn't mean that they're actually ready. You need to go through and verify that, because if you do the tab water balancing and it's not ready, then you will be wasting everybody's time because it doesn't work that way. So I always make sure I go to the job, I walk the job, the whole job, to make sure everything's ready for me before I start. When you're starting to do the water balancing in a closed system, you have to make sure that the system is full of water. And the way that we fill everything up is we use the city water or the water from the source to make sure we fill all the pipes. Obviously, then we treat that water, but we have to make sure that we use the water to fill the pipes in the right way. And we need to make sure that that is at the right pressure. So, in order to do that, one of the first things you do as a tab professional is you make sure that you set the pressure reducing valve to maintain that proper pressure in the system with all the system and the pumps off. So you make sure all the valves are open, everything's off. You set that PRV at the right pressure to make sure everything is working properly. And the way you do that is you figure out the formula, the piping height in feet, and it just depends on how tall the building is. Most buildings are 1 or 2 or 3 stories, so you're going to set that PRV at whatever that height is, plus a little extra safety for hot water systems, and then convert it from feet to PSI and make sure that you set that PRV at the right pressure so that the water is always keeping the pipes full. Because if the pipes aren't full of water, they end up being full of air, and air is not good for pumps, right? So we make sure that we set that PRV in the beginning to make sure everything works. Most chill water systems, hot water systems, have an expansion tank. It's typically preset from the factory for a normal 1, 2, 3-story building, so you'll be fine with that. Make sure that works. Again, you're pre-setting, pre-filling out all the paperwork to make sure that everything is documented on what you find and what you start with. And then as you do your tab work, you fill in the test part of that. You have to make sure that the pumps are working properly. Part of that is starting up the pump to make sure it's flowing properly, but you also have to make sure the pump is aligned properly, like the shaft is aligned with the pump from the motor, and that you don't have any excessive vibration. A lot of times you'll have a mechanical technician checking for that alignment and making sure that that vibration of that shaft is okay. If it's not okay, then that technician will end up putting in some shivs or some shivs there to make sure that the pump is set up correct and is operating right. So important to get those pumps to operate well, because pumps are usually very big and they're very powerful. And if they start jumping around, bad things happen inside the piping plant. So that's very important to get set up very early on. Then you're going to start in the chilled water plant. Most of the time in bigger projects, we're always going to deal with primary, secondary chill water plants. It is becoming much more popular now to do a primary plant and not have the secondary, but it's probably, I don't know, probably only like 10 or 15% of the projects are going only primary. Most of them are still going the old primary, secondary pumping systems. So that's where we do most of our work, and we try to teach that in most of the projects. Obviously, if you're just doing primary, it's a lot less work and a lot easier to set up. So that's how that works. So here we go. We're going to step through the process as we go through the plant, step by step by step. So we start off making sure that we set up the pressure taps and the gauges are all installed and working. And we don't use their gauges. We actually unscrew all of the gauges on the job, and we use our own instruments inserted where those gauges go. So we make sure that all of our equipment is connected, and we take these gauges and then set them off to the side. So let's start with the primary. So we start with the primary pumps of the system. We do what we call the block off or the shut off to verify the impeller size. So basically all we do is we shut the valve on the discharge side of the pump and then let the run the pump at the normal speed, and then we look at those pressures. So we block off the pump by deadheading it, and then we compare it to the pump curve data to make sure we have the right impeller, for the right pump. That's very important. The first thing we do every time. We check it as far as the pump curve, make sure we have the right impeller, and then we're good. Then we throttle the VFD, or sometimes we use a triple duty valve. We end up throttling that in order to make sure we get the right chiller evaporator barrel pressure, DP within 10% of the design, and make sure that's all set up. And we do that on the primary side because getting the right differential pressure across that chiller barrel is so very important. We set it a little high, we go like 10% above to start with, but we make sure that chiller barrel has its differential pressure. Because if a chiller barrel does not have its differential pressure, the chiller barrel does not work, the chiller doesn't work, bad things happen. So the most important thing we do in the beginning is make sure we set that primary pump to where it operates in the correct way. Now we look at the chillers, and here are the two chillers, and we make sure that those are okay, make sure that differential pressure is okay. We take those readings to verify it, and then we record that DP and that percent speed of the variable frequency drive, and now that becomes your setting for the VFD of the pump on the primary side. And then many times what we do is we will write what that speed is, and then we will set the maximum speed of that pump at whatever hertz or whatever speed we set it at. And that way the pump can never go higher than that. And that's important, that you don't over pump the chiller, very important. So that's how we do that on the primary side. And then we look at the secondary pumps, right? So now you've got all of this set up. So all of this is going to be right and correct. Now you're going to move down to the secondary side. It's the same setup. We set the block off, we shut off to verify that side. But what's important to note is that on the secondary side at the units, the new technology control valves are really, really good. They are so improved that many times those secondary pressures are working per the design, and they design that right into the control valve. So a lot of times we don't have to go and check those. but still we make sure that all the cleaners are strained, all the cleaners are changed out and that they are clean, all the valves are wide open, and everything's ready to do that secondary side. So it's the same setup that we did on the primary. We block it off, verify that impeller is correct, making sure, of course, that all of those valves are open and working, and then we can set the secondary pump for the flows that we want on the secondary side. Again, we compare it to the pump curves that we have in the submittal to make sure that we're on the right track, and then we set that flow at the secondary side depending upon what the flow is that we need out in the space. We can also at this time instruct the building automation contractor on what differential pressure we want to run the chiller plant or run that secondary side out. Typically, they will have a differential pressure sensor set at the end of the system. And typically, it's set, if it's at the end, it'll typically be like 10 psi or 15 psi. So, but we will calculate back wherever it's from, and we'll end up instructing the building automation contractor on what that setting needs to be. So we'll throttle that back and then make those adjustments. The way we make adjustments on the secondary side, again, preferably we're setting the variable frequency drive at the setting we want, but many times, you know, we can also do it by using the triple duty valve. The triple duty valves, you know, are problematic in that, you know, they use energy. So triple duty valves, they have a lot of functions. They operate as a check valve, an isolation valve, but they also can be used for balancing. But if you have a variable frequency drive, you do not want to use those for balancing, because as you close that valve, you're burning energy, right? You're burning energy. So the better way to do it, if you have a variable frequency drive, is to, okay, use it as a check valve, use it as an isolation valve, but do not use it as the balancing. Use the variable frequency drive to make your speed settings so that you're not burning the energy and you're actually saving that energy by using the variable frequency drive. So it is something that engineers, design engineers, are still installing the triple duty valves just because I guess everyone's just so used to it. And they don't want to break tradition and not have the triple duty valve. But at some point in the future, I think that will stop, because triple duty valves are expensive. And if you don't need them, why install them, right? So I think that's, you know, that's something to come in the future. But right now, we typically have triple duty valves and we have VFDs in chiller plants. And that's just the way it's going to be for a while. The other thing we worry about in chill water systems is what we call low delta T. Low delta T is caused by, you know, running too many pumps when you don't need them, running too many chillers when you don't need them, and you're recycling that return water back, and you're getting that low delta T back to the chiller plant, and it causes a lot of trouble. So, I mean, really, the best way to solve that is work with the building automation contractor and make sure he's sequencing the chiller plant in the correct way, and that will usually cure that problem. But this happens a lot, because a lot of people think, well, if one chiller is good, two chillers is better. But that's just not the way it really works in reality. If you can get away with running one chiller and getting your very large delta T through the system, that's better than running two chillers and getting a low delta T. Much, much better for everybody concerned. So now we're going to start balancing the water distribution system. And the way we do that is we look at the system overall. Now here's the chiller plant that we just talked about, right? And from the chiller plant, we're going to go up and go out to the system. So here we go. Here's the main coming out of the chiller plant, and it's going to come up and feed these two headers, one at 2,000 and one at 1,500 GPM. So like we did with the air, we're going to start at that highest number with the highest flow, and we're going to balance the one that has the highest flow. So here we go. we're going to go to the one with 2,000. And we're going to balance that out to what we're looking for up here. And then we're going to go to the next one and balance that out. Now we have the water balance from the main into the two headers, and we're in good shape. Where do we go next? Now we go up into the risers and we see what the risers are doing, and we pick the high riser, right? Here's the two risers, and look, there's our high number in the riser. So that's where we're going to start. That's where we're going to start our water balance. Where we're going to look at those branches and move our way down. So we start at the 400. We balance that one out. We forget about this. This is gone. So now we're going to come here. We're going to come here, and we're going to come here, because this is the next biggest, the next biggest, and the next biggest. So now we've taken all that water and we've balanced this side of the system. So now we're done with this, right? We're done here. Now we're going to move over here. We look at these numbers. Boom, we got a 350. It's the high one. So we're going to do the 350. Then we're going to do the 250, which is here. Then we're going to do the 200, and then we're going to do the 150, and then we're balanced out, right? So what's reality? What reality is, in these days, that there's a lot of what we call pressure independent control valves, or PIC valves, that I showed you pictures of before, and those are all set up at a certain GPM. They're already balanced from the valve factory to only do X amount of GPM. So having to go to each individual branch and set that GPM flow is really not that necessary anymore. So the good news is for the tab professional that the new technology is doing a lot of our work for us in advance. So it's happening. But the other part of reality is these new control valves with all these fancy systems and all that, they still need to be checked. Because what's happening right now in the business is these are all designed, for example, this is 50 GPM, and this one's set for 35 GPM from the factory, and that's it. But what's happening in the industry is some of these are calibrated at the factory and some are not. The controls contractor or the BAS contractor has to pay the factory to do that. And in many cases, they don't pay. And if they don't pay, then the factory does not do that. So if the factory doesn't do it, then the tab professional, the tab technician, has to go out in the field to each one of these valves, and they actually have to do the setting. And that happens to us now on at least half of the jobs are not set at the factory. That's what we're finding. It's just, for whatever reason, the controls contractors don't want to spend the money. They charge $30 a valve at the factory to calibrate, and the control contractor says, nope, I'm not going to pay. And they don't tell anybody, so we end up having to do it when we get on the job. But that's just the way it is. That's what reality is. It's changing. More and more we're finding out, and we're making it more mandatory for the control valve manufacturer to calibrate it at the factory, and we're making sure that they have to document and certify that. But for the last couple years, we've been finding like half of the time they're not calibrated at the factory. So when they're not calibrated at the factory, it's still our responsibility to make sure that that's done. So now you've gotten all of the water side balanced, because you started at the chiller plant and you went from the mains to the headers up to the branchers and the risers, and then you went to each valve, and now you're all done. So now you've done your water balancing and you're ready for the tab report. So like we talked about in commissioning, there are many of the same companies that are providing software to put together those reports for you. But again, you have to pay for that software. A lot of companies don't want to pay for it. So if you have a software system that'll do it, fine. If you don't, then you still have to put together the tab report. And the tab report is most important. For the tab report is to make sure that you have a section on deficiencies and how things are working and not working. Now again, you're going to show the deficiencies and you're going to show that they've been fixed, but it's good to know that there was deficiencies and that you document them getting fixed. And then you have a lot of different data sheets for test and balance that you include in the final report. They all look a little different, but it's the design condition versus your actual test condition documented to make sure that in your final report you have documented everything that went on in that project. And there are many forms. There is a form for every piece of equipment and how that works. And what we like to do is we like to have a suggested format for the information flow. So we like to see a cover page start. Then we like to see the list of comments and deficiencies, the certifications and signatures, any performance guarantees, licenses used, all your calibration certificates for all the instrumentation, and then finally, at the end, we see the tab reports and the summaries. But that's a standard format that we like to see when those reports go out, and that way they're 100% complete and they're standardized so that all of everybody's tab reports kind of look the same and everybody, is doing it the same way. So that's testing, adjusting, and balancing for both air and water. I know it was a lot of math and a lot of calculations, but that's just the way it is with TAB. That's what it's all about. So thank you very much for inviting me to talk to you about TAB. I really enjoy that part of the business. It's very challenging, and it's a very good thing. I hope that here in Thailand, the T-TAB will work more, and if there's anything we can do to help you get connected with any of these companies that will certify your technicians or engineer, we'll be happy to hook you up with those people. They're very excited for you to come work with them, and it'll be a lot of fun. So with that, I want to answer any questions you have on the water side of test and balancing before we go to our next subject. So with a raise of hands, somebody asked me some questions about the water.
I have a question because according to your presentation, the way you do the balancing is always touching the highest volume, right, for both air and the water size. Is there any other way to do the balancing apart from this? Because I heard some company from Australia, for the water side, sometimes they do backward balancing, not forward balancing. Also the air side, yeah.
Yeah, well, I mean, in engineering, we like to say, we can do anything you want. We can figure it out. If we start at the low end and work for the high end, whatever. But this is the problem. If the system is designed properly, let's say you have 1,000 CFM or 1,000 GPM, that's all you got. So, when you go look at the distribution system, it makes sense to me that you start with the high one, right? Because you're trying to take that high one, balance it down so you have more water for everything else. If I start at the low one, then, I may not have, when I get at the end, I may run out of GPM or CFM because, I still got the high one out there taking all things. So I think that's why they want us to start at the high end and work down. But I think, engineers can figure it out. If I start at the low point and I start running out of CFM or GPM, then I can switch to the high and force a little high, down in the, But the problem with that is you always have to go back and double check. If you don't start with a high, then if you're going to start mixing and matching, then you're going to have to go in the end and do it, and you're going to have to do it a second time. If you start at the high first and kind of proportionally balance it down, chances are you're going to be correct the first time and you don't have to do it the second time. Yeah, because you want to kind of do it in one round instead of, the best practice is for you to do it once and then kind of do it again, but, We always start off saying we're going to do that, and then we run out of time. You know, always, every time. Or there's another job calling, and we have to go to another job. So that's just the way it is. But yeah, I mean, that's why they tell you to start high and go low. Questions? Questions? All right, we got a question.
I saw your presentation that you said that the flow meters need to be calibrated. When we install the flow meter like the inline magnetic flow meter, how do we calibrate it? The flow meter?
How do you calibrate it?
Yes, because we cannot take it out. Right.
So the question is, how do you calibrate a flow meter when it's in the pipe or in the duct, right? So we just, as test and balance professional, the flow meter, whether it's water or air, it comes pre-calibrated from the factory, okay? Pre-calibrated. But that's in a laboratory and that's in a factory. Now you come to a job site and you put it in a pipe or you put it in a duct, and instead of 4 turns, there's 8 turns. Instead of putting it in the right place, you put it in the wrong place. So a lot of things happen on a job that's not the perfect condition of a factory. So we, as a test and balance professional, have to hook our instrumentation up to it and then read what we read and read what the device reads and then calibrate the device that way. You know, most of the time, you know, we're very near to the factory calibration, but still, we're required to be within 10%. So, you know, if it's outside of that 10%, we have to calibrate it down to make sure it's okay. So we're supposed to do that on all water and air flow meters. Thank you.
How about the accuracy? Can we calibrate to verify the accuracy of the instrument when we install?
You calibrate to the accuracy of the instrument? You mean the accuracy of my instrument or the accuracy of this other instrument?
The install instrument.
Okay. Yeah, because we do calibrate to that accuracy. Most of the devices that are installed are required to be within 5 or 10% accurate. And so we also are required to do the 5 and 10% too. So yeah, I mean, our accuracy, that accuracy can be a little bit off, but yeah, we have to try to get it within 5 or 10% of what that design value is. That's what we're charged with.
I think his question is about when he reading the data from the instrument, the flow meter, how he know that that number is accurate, reading accurate. I mean that how he will know that after we install the flow meter, when they're reading, that reading is correct, something like that.
Yeah, but that's, we calibrate it when it's installed. So the reason you know it's correct is because we are now calibrating it installed. Previous, it's calibrated at the factory in a laboratory. So, and that's under perfect conditions. Now you get in a job and it's not perfect anymore. So we use our instruments to calibrate it as it is installed in the system. So that's how you know that it's actually installed and operating correctly and the calibration is correct. Any other questions on water balancing? Water. All right. So we have one subject left. We're going to take a 5-minute break, you know, for us to load it up, and then we're going to start with the next subject, right, that we're talking about. Is that okay for everybody? Very good. The government says that we should do it. The government, the US EPA, says we should calibrate and keep everything working and operating per per its practice. The manufacturer recommended practice says that we need to clean those devices, make sure they're operating properly, and then basically practitioners, people that actually sell it, will tell you that yes, you absolutely need to keep the filtration of the air that hits their devices clean before it hits the airflow monitor. Otherwise, their airflow monitor will not work right. What engineers tell me, or what practitioners tell me, is they go, well, you know, we really don't need filters on the outdoor air because we expect the maintenance and operation personnel to clean those airflow monitors every 6 months or a year. Guess what? It doesn't happen. It doesn't happen. They don't clean them. They don't work. And once they let it go, and once they're bad, they're bad. They don't get any better. They're bad. And when you try to clean something when it's really, really, really dirty, it's gone. It's gone. It's never going to come back to what it is. So what I did is I went out and I got contractor opinion. This is a contractor that happens to do the schools that we actually did the case study on, but he's a contractor, he's an engineer as well, and he agrees, hey, in all of his career, he sees this happen all the time. He says, we install airflow monitors, we regulate the amount of air that comes in, we test it, we balance it, and then 6 months later, it doesn't work anymore. We have a lot of support for this. Both the contractor and the owner agree that we have to do that. And we use this as a test case to make sure it happened. We have the voice of an architect, a senior architect, Don Copy, and he says that, you know, all of these projects, they are warranted for a year, and if they don't work 100% after that year, they need to be fixed or replaced. And what I'm saying is, these filtration, this non-filtration of airflow monitors, it doesn't last for 6 months. So really and truly, at the end of that period, the contractor should be asked to go ahead and replace the systems that don't work. But the architects that I talked to agree. So what I'm saying is, work with your tab professional and make sure that those calibrations are done during the tab process. Do not trust those out-of-box calibrations because they're not correct. Those are all done in a laboratory, and so it doesn't apply to real-life systems. And that tab and that commissioning professional will help you get there. What I'm also saying is location, location, location is very important. These flow meters need to be installed in the right place the first time, and once they're tested, that's fine. But as we go through the project and we look at how they're working, we have to continue to look and make sure that they're operating per the design and they get in the right place. That starts with the outside air louver design itself. This engineer who designs these systems wants to make sure that these louvers are properly designed to keep the velocity low enough to avoid any kind of moisture coming into the system and therefore hurting the airflow monitors because they get wet. Also, if they don't design the louver properly, that water will also get on the filters and they will get wet and they won't work anymore. So it's important that we maintain this louver design, you know, per this specification to make sure that everything is done right and that the systems coming into the outdoor air work properly. I have a job right now that the outside air louver system is designed so bad that the velocity coming in of the outdoor air is so fast that now it affects the actual operation of the cooling coil. Because as you know, cooling coils like a certain velocity across them. But when the outdoor air is not designed properly, that velocity is very much higher through the outdoor air, which increases the velocity through the coil, which makes the whole entire unit not work right. So, I mean, this kind of thing is very important. Very important to make sure. And then you got to make sure that the airflow monitor and that the return air damper positioning is correct as well. Because what happens is that many people will, the airflow monitor will try to maintain a certain airflow. Let's just call it 500 CFM. But if the airflow monitor can't see 500 CFM, what people do is they start closing the return air damper, which forces, more air, through the outside air damper. But then what it also does is it increases the velocity of the return, which again increases the velocity of the system through the coil, which again, if these systems are not designed properly and operated properly, we have a lot of more problems than just the wrong outdoor air. We typically have problems with the unit and how they're cooling or heating because the velocity through those coils are much, much worse. So we have to make sure that these airflow monitors are installed in the right place. Here is the airflow monitor, here's the outside damper, here's the airflow monitor, here's the outside air damper. These are installed in the wrong place because what you cannot do is put an airflow monitor after the damper. Why? Because this damper is modulating up and down, open, close. And so this airflow monitor is seeing this crazy pressure change all the time. You can't have that. You have to put this airflow monitor probe before the damper in order for it to work right. Otherwise, it just doesn't work. It's high, it's low, it's high, it's low, and the control system can't keep up with it. So even if you have an airflow monitor that's protected and clean and operating, if you put it after the damper, it's not going to work right anyway. So, I mean, these are things I see in the field all the time, and I've seen them year after year after year. Nobody seems to care. But we have to start caring. We got to make sure we do what we do and we do what we do right. So what I tried to do in this article was do a case study on a school that I did to prove that this happens. But, it happens all the time. It's not just this school, it's jobs that I've been doing for 20 years. They're all the same, and it's still jobs I'm doing now that are still all the same. But this project, this case study, was a K-12 school in Florida, and a very hot and humid climate. And the outside airflow meters and all those, they were all correctly calibrated at time of construction to meet the design specifications. I was called into the job a year later after 1 year of service because there were a lot of deficiencies going on and the building was getting a tremendous amount of complaints about everything: cooling, heating, airflow, ventilation, everything. So I was called in to do that. So let's look at specific issues and deficiencies that I ended up finding. This is kind of a listing of the air handling units. This is the design outside air CFM. This is the outside, damper flow, the percent change, the percent open, and the return air damper percent open. So as you can see, there are varying designs of deficiencies going on. And I'll go through each one by one. So what happened here was, you can see 0, 0, 0. So what happened is this outside air damper is, what happened a year later is these outside air flow meters are not working. And so what they're saying the flow is so far over the design set point that they're saying, oh, I have too much flow, so I'm going to 0. So now those areas have 0 ventilation. So they're now negative, right? They're negative. And then on the other side, and here's just an example of what that looks like as far as on the BAS, right? And then on the other side, now the outside air dampers are all at 100% because now the airflow monitor thinks that the flow is way under the design. So guess what? Now they go and they open themselves up 100%. So now you've got 100% outdoor air, and so what you're getting is you're getting as much outdoor air as that will pass through that damper, which is probably 2 and 3 and 4 times the design. So now you got a building that's being flooded with outdoor air, which obviously can't be cooled properly because, no coil is going to handle 3 and 4 and 5 times the amount of outdoor air, right? So yeah, I mean, it gets crazy. So this is just more graphics, to show you how that works. But the impacts to the owner are very large. Inaccurate ventilation to affected occupant spaces due to erroneous readings, additional costs because those are much larger than necessary, and the over and under pressurization of the building, the doors staying open, more and more and more. There are just so many problems that this causes. Demand control ventilation. If it's being used, then all of that doesn't work anymore at all. So the building is not operating at all. So when I first got into this building, it was like the complaints were there were just so many, we couldn't help it. But we went through and we looked at all this and we said, we've got to fix it. So the first thing we did is we tried to clean them. But because they were in the airspace and they were so dirty, every time we tried to clean them, it didn't work. I mean, a couple, 2 or 3 of them did actually work after that, but the majority of them didn't. So again, the owner is having to have an increased maintenance cost because now they have to replace those airflow monitoring devices to make sure they work. And then, of course, they have an increased risk to occupant health impacts, illness and disease because the ventilation is inaccurate or deficient. So the owner is having to pay for all these things that they should not have to pay for if this thing was designed and installed correctly. Now we're drifting out of code compliance for the ventilation, we're increasing energy use, we're losing productivity, and the designer or installing contractor is now got a bad reputation. And it's not all their fault. You know, they weren't told to do this. You know, the outside air was not filtered in the design or the construction, so it's not really their fault, but they still get a bad reputation because they're involved with a bad job. So it's a bad job for everybody and everybody suffers. So we did attempt to clean the airflow monitors, but it really didn't work. I mean, a few of them did work, but for the most case, they didn't. They didn't work. And then over time, they all fouled out and we were in trouble. So what happened was on this job, we had a good relationship with the contractor. So the contractor was able to convince everybody involved that they should go ahead and reinstall the airflow monitors correctly. And that it probably would have cost us $15,000 to do that. But because the contractor was friendly to the owner, they ended up doing that. The building was brought back into ventilation, rate compliance after we retested and recalibrated, but you know, nobody did anything about the outside air, so guess what? Right now, that building is still the bad building that it was 6 months ago because it's been 6 months, and those airflow monitors that were installed are now dirty again. So it doesn't really work. So yeah, I mean, we fixed that project, but you know, it's back in the same case now. So, you know, at the end of the day, I guess we didn't do too much work. But the easy solution is to figure out how to add the outdoor air. And we can do that at a very reasonable cost. And what happened is this owner decided in their next project that they would actually put outside air filtration in the outside air before the airflow monitor. And so we're doing it on a project that's just like that. And we figured out that it would cost approximately $9,000, which is $643 per air handler or 0.23 per ventilation CFM. That's just not that much money, right? It's just not that much money. In order to assure that $15,000 that could reoccur all the time, that $9,000 is not much. So therefore, the cost of not providing it is not a smart thing. If the building lasts 15 years, those airflow monitors could be replaced up to 5 to 7 times. And 5 to 7 times 15,000 is a lot. The cost to do it right is only $9,000. So the payback is very quick. So it makes sense to do this on every project so that all of these airflow monitors will continue to work throughout their life. So the market has great products to accomplish our goal. We have demand control ventilation based on CO2. We have space pressurization. We need to maintain good indoor air quality better control of moisture, and maintain those code ventilation rates and energy conservation. That's what we're trying to do, and the simple solution is to make sure that we provide good filtration for that outdoor air. So, in conclusion, the designer and the engineer can play a huge role in making all this work. All they have to do is take good, reasonable care in the design and installation to make sure that A, that the airflow monitor sensor probes are located in the correct position, but also that they are filtered. They need to make sure that the louvers and the duct designs are correct, and make sure that they bring this filtered louvers, these duct filter assemblies into the construction, and that they're done. It's simple. Just do it and we'll solve the problem. It's really not a big deal. So my conclusion is, please protect those airflow monitors. The payback is really good, and it just doesn't cost that much to do it the right way. So with that, I just want to make sure, with some final thoughts, that the architect and the engineer, the contractor, TAB, and commissioning professionals can work together to achieve these really good outcomes. Everybody wants the same thing. Everybody wants a good and a good job at the end, and we can all work together to do it. Thank you very much for allowing me to speak on this subject. Obviously, I'm passionate about it because it's just a complete waste of money and waste of time to spend $15,000, $20,000, $30,000 on good airflow monitors to have them go bad in 6 months, and they're just not of use to anybody anymore. So thank you very much for letting me talk about it, and let's open it up to some questions about this subject or anything else that you want to talk about. So raise your hand and ask your questions. We're getting at the end of the day, right? We're questioned out.
So the problem still not solved yet, right? The same problem keep occurring every 6 months.
Yeah, I mean, what happens is, I mean, as much as I campaign and tell my engineering friends that they need to stop doing this dumb thing, is they keep coming back and telling me that, well, the maintenance and operation people are supposed to maintain the project. So I don't want to spend money on extra filters because the maintenance and operation people are supposed to do that job. And I'm like, come on, man, that's just not reality. You know, these airflow monitors are installed in locations that you have to get up on a 10-foot ladder to get to and to clean. You thinking a maintenance guy is going to climb a ladder, you know, and do that? It's just not happening. It's just not happening. I mean, people think that's happening. It's just not. And filters are, and they say, oh, well, filters cost a lot. Well, yeah, they cost a lot. But these days, most owners of facilities, they hire a company to change filters. And they come in every 3 or 4 or 6 months or whatever, and they change all the filters. So having a couple extra filters on the outdoor air is not going to cost that much money. It's just not. So I don't understand why people don't do it more, but they don't. And I'll keep trying to convince them to do it, but that's where we're at. Any more? Any more? All right. Well, thanks very much for inviting me to come and talk to you. I've really enjoyed my time here, and if you ever have any questions or comments, you have my email, you have whatever you want, please contact me, and I will answer it the best I can. Thank you.
ครับก็มาถึงช่วงสุดท้ายของการสัมมนาในวันนี้นะครับก็เดี๋ยวขออนุญาตเรียนเชิญครับคุณอภิชิตครับพี่อภิชิตของเรานะครับเป็นตัวแทนจากสมาคมปรับอากาศแห่งประเทศไทยนะครับเป็นผู้กล่าวปิดการสัมมนาในครั้งนี้เรียนเชิญพี่อภิชิตด้านหน้าครับขอเสียงปรบมือด้วยครับ
ครับก็สวัสดีทุกท่านนะครับก็ถึงเวลาเพราะว่าผมว่าการ commissioning ที่เขา มาอบรมเราเพราะเรากว่าจะเชิญเข้ามาก็ค่อนข้างลำบากจากสหรัฐอเมริกานะฮะการคอมมิชชั่นนิ่งก็ทั้งบาลานซ์ทั้งด้านแอร์ไซด์นะทั้งวอเตอร์ไซด์อะไรต่างๆ ที่เขาได้แนะนำเรานะฮะก็ยังไงก็แล้วแต่ถึงแม้จะเดินครั้งแรกก็จบก็จริงแต่ว่าสุดท้ายก็ต้องมีการ maintenance แล้วก็การปรับadjust ใหม่ทุกครั้ง calibration นะฮะก็ต้องทำเรื่อยๆแต่มันก็มีแพทเทิร์นที่มาตรฐานให้เราใช้นะครับเพราะเขาให้ความรู้ที่ค่อนข้างดีนะครับเป็น DL ที่เราเชิญมาหลายครั้งนะฮะก็เป็นผู้บรรยายที่ค่อนข้างชำนาญมากนะฮะด้านนี้นะก็ในการ testing แล้วก็balancing นะฮะก็ adjusting ก็ balancing เป็นแท็บนะฮะที่เป็นตัวย่อก็ค่อนข้างดีนะฮะในการบรรยายนี้ครับก็ขอให้เราตบมือและขอบคุณท่านอีกครั้งหนึ่งครับขอบคุณครับสวัสดีครับ So we thank you very much that you spend your time valuable time to education our Thailand chapter here so welcome you thank you very much thank
Very nice. Thank you. Thank you very much.
Can we give some little token to you yes
Yes, I like tokens.
อ๋อ
Let's say see the some Thailand chapter
Okay, thank you. Thank you very much. Appreciate it. Thank you.
ก็เดี๋ยวเชิญทุกท่านมาด้านหน้าเวทีครับเดี๋ยวขอถ่ายรูปรวมเก็บไว้เป็นที่ระลึกหน่อยนะครับ